Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is derating of connectors. What do you need to consider? Our speaker today is Stefan Bechle, who is working as Field Application Engineer in the field of electromechanical components at Würth Elektronik eiSos. He will hold today's webinar and also answer your questions. Before we start, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. And if you have still any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation as well as to the recording of today's webinar only in the next few weeks. And now I will hand over to our speaker Stefan, and I wish you an exciting webinar.
Yeah, thank you very much, Markus. And hello all together. Thank you for joining our webinar at Würth Electronics. My name is Stefan Bechle. I'm Field Application Engineer for the electromechanical parts. And today I have a topic for you. If you are using connectors in the power direction, if you need a lot of power on your PCB, it may be that you have to deal with temperature rise at your connectors. And now I will present you a small presentation about connector temperature rise and the derating, and I will give you some hints and tricks what to do when the temperature is too high in your application. Let's have a look on our agenda today. First of all, we will have a look on the point how to find the right working current of a connector. So if you open a data sheet of a connector, you will read about the working current, but how is this working current designed and found? I will show you in the first point. The next step will be consequences of a too high temperature. Yeah, we have many different materials on our connectors, and they are all influenced of high temperatures. And we will see this at point 2. And therefore, we have also to look a little bit on the temperature rise rules. And now we see the situation. We have too much energy, too much heat on our connector, on our cable. What can we do against it? How can we transport the heat away from our application? How heat is dissipated? We can do it, for example, with a cable. So we have a look at the point heat in a cable. Then I will show you some tricks which are possible to reduce the heat in your application. And at the end, this will lead to the so-called derating curve. And if you respect the derating curve in your application, you're always sure that the application cannot get too warm. If it gets too warm, I will show you some pictures of destroyed connectors at the end, the small connector horror show for you. And at the end, finally, what to remind in your design when you're dealing with power. So what happened here? This connector was used in a wrong way. It was used in a closed box with a too high current. Too much thermal energy has to be dissipated by the connector because of the too high current. So for the energy, it was not possible to be dissipated in the air because it was in a closed box. It could not disappear through the air. And at the end, the energy was stored inside and increased temperature without any stop. So temperature at the end was so high that the plastic melted. So the plastic material is completely destroyed of this connection and obviously cuts the circuit. And this should not happen in your application. Therefore, we have a look at our derating curves. So how are we finding our working current? Let's have a look on a data sheet of a typical power connector. You can see here a 3-pole terminal block. I think it's a pitch of 7.62 or something like that. A typical one for power connector. And if you read the data sheet, you will find something like the operating temperature. It's from -40 to 105 degrees. So how do we find the working temperature at Würth Elektronik? It's just related to the plastic material. In this case, we have a terminal block made out of a polyamide, PA66. And this PA66 is suitable up to around 125 degrees Celsius. And we have always a security margin in Würth Elektronik. So we specify this product up to 105 degrees Celsius. Well, more down you can read the current rating. And we have a current rating here with 20 amps. But how can we fix the number 20 amps? How do we come to this working current? Therefore, we have to look first at electricity and temperature rise. So our connector has also a resistance, so it behaves like a resistor in the circuit. And when we have a resistor and when we have an ambient temperature, let's call it room temperature, around 20 degrees, it's the temperature T. And everybody knows when we are sending some power, some current through the resistor, it heats up through the Joule's effect. And this heat is the delta T, and it has to be added to the normal temperature, to the room temperature, to the ambient temperature. And this is the same principle as we have in a heater, in an electric heater on the wall. So how does Würth Elektronik design the working current? Therefore, we have to do a test, a so-called temperature rise test. Behind that is a standard existing. It's the EIA 364-70. And we will specify this connector first regarding the UL specification. Therefore, we have the UL 1059 specification, and it says the connector has to be tested with a 3-poles connector. And of course, the working current has to be put in series. Then we put on 20 amps on this connector until we reach a stable temperature. We have to do 3 measurements, each 5 minutes, and the temperature has to be equal ±1 degree Celsius. And now we have a difference if we want to specify after UL or after VDE. If we want to specify after UL, the connector is allowed to get a temperature rising of 30 Kelvin. This is written in UL 1059. VDE is a little bit different for the European market. It's allowed to heat up the connector up to 45 Kelvin. So how do we do this working current measurement? Therefore, we need something like a climber chamber. You can see it here on the right side to avoid the air floating around the product. The measurement is done with so-called thermocouples. The thermocouples are wires of different materials, 2 small wires of different materials. And if we have a different temperature on these 2 materials, there's a little voltage released. So we can measure the temperature of our product. And those thermocouples have to be mounted on the hottest point of the connector. Let's have a look how this is done. So you can see we have our 3-pole connector here, and the thermocouples are mounted at the hottest point in the middle of the connector at pole 2. Then we have a specified electric assembly of 50 centimeters length. It's also written in the UL standard. And the TBL is tested with 20 amps. Our idea was 20 amps should be okay for the connector, so we tested it first with the 20 amps. We have a little bit of margin in because the wire used for it is a AWG12, and for AWG12 the maximum current is 20 amps. That is one of the reasons that we do not increase the current rating of the TBL. if we only use the I square rule, we could go up to 22 amps, but the cable is not allowed to go up to this. So let's have a look at the warming. We said UL says it has to be lower than 30 Kelvin. And we measured a temperature of 46.5 Celsius minus the ambient temperature of 21.7 degrees Celsius is a delta T of 24.8 Kelvin. That's okay to specify the connector for 20 amps. So what happens when the temperature gets too high? There we have to look on the different materials of our connector. First, we will have a look on the base material. In most cases, it is a so-called copper alloy. And when we talk about copper alloy, we have to respect the corrosion. And if we have higher temperatures, it increases the corrosion speed. And if it increases the corrosion speed, it increases again the contact resistance. So this goes around and around and around and heats up the application more and more. So this is really dangerous. I have an example for you for brass. It's also a copper alloy, and contact resistance increase versus the temperature. And when we have a look there on the graph, we can see that each 50 degrees Celsius, the resistance rises around 20%. So this goes around and around. The corrosion speed increases, the resistance increases, the temperature increases, and the corrosion increases. So this is really dangerous for applications. But we have to take in consideration more regarding, for example, also the plastic material. If we do not respect the plastic material, we have pictures like this. So the plastic material changes its color and it's also brittle. It can break after a while. What do we have to respect here? It's the so-called RTI, the relative thermal index of our plastic material. And this is different regarding the plastic material we use for our connectors. And as I told you before, for the polyamides, it's around 125 degrees. That means if we use a polyamide below 125 degrees, you can be sure that it will last for a long, long time. If we go higher than 125 degrees, the material can change its colors and it can get old very fast. The next thing we have to consider is the metal relaxation. Most of the connectors are established with a spring inside, so it has to fix the mating part. And there a relaxation happens after some time. Okay, it is a long time. It goes up to 10 and 12 years. And it also depends on the temperature of the product. So you can see it on the different colors here in the graph. If we have 20 degrees Celsius on our connector, so it will last for a very long time. But if we put on 150 degrees on the connector, it will go faster with the aging, the relaxation will be faster, and then the resistance goes also up again. So therefore we have to have a look on the temperature rise rule. We have our resistor and our temperature and our heating temperature, our delta T, and we have to have a look on the Joule's law. It says power is the resistance multiplied by the square of the current. And this is really dangerous because we are talking about the square of the current. Means temperature rise is always proportional to the square of the current. So what happens if you put on a connector or on a resistor suddenly the double current as before? We just made an example. We measured an I1. We gave 50 amps on the connector, also on this terminal block, and it gives us a delta T1 of 15 Kelvin. Then we doubled the current. we gave an I2 at 30 amps. There, the result was a delta T2, and it has to be calculated. 32 square divided by 15 square multiplied by 15. And then you have 16 Kelvin temperature rise, 60 Kelvin temperature rise. So that means if you double the current, you have 4 times higher temperature rise. This has to be considered in your application. Therefore, we are doing our derating curves. So, the theoretical calculation may be something, but is it really true? So we had the calculations here in our graph done at 20 amps with a delta T measurement, as we saw before. It's around, here it's around 24, 25 degrees Celsius, which is allowed for this connector at 20 amps. And now we put on the next curve, and the measurement curve, as you can see, is exactly the same as the calculated curve. So it's really the truth. If you put on double current, you have 4 times higher temperature on your system. What do we have to remind altogether? Each resistance releases heat under current, and the working current is designed regarding UL with a delta T lower than 30 Kelvin, and regarding the VDE standard, a delta T lower than 45 Kelvin. And we have to respect the maximum working temperature of our connector because of the plastic material, because of the RTI, relative thermal index. And the temperature rise is proportional to the square of the current, so we have to take care of the current, not to apply too much current on our connectors. It will destroy the whole application. But what happens if we have too much thermal energy on our system? We have to find a way to dissipate the heat, and therefore we have different possibilities. First, we have a look how the heat is dissipated generally. Therefore, we just made a little fire, and the first heat which is dissipated from the fire is so-called radiation. And the radiation is heat dissipation through light emission. That means light frequency depends on the temperature. It's the principle of a thermal camera, for example. And also the way how the sun heats the earth through billions of kilometers of frozen vacuum. But we have more different dissipation. We have also the convection. Convection is the dissipation through the air around a heat source. It's released to the natural movement of the air, which will go up when it gets hot, as hot air, and cold air will go down again and will be heated up again and then come up again. If you stop this movement, like putting your connector, your application in a closed box, then the energy will be stored inside of it, and the connection is no more possible in the closed box, and the application will get too warm probably. But that's not all. We have a third one, a really important one, and this is just the conduction. The conduction is the dissipation through touching the heat source. In that case, what do we touch? We touch, for example, our cables, we touch our PCB, and we will see the importance of the wire length in the next slides of our presentation. So we do not have a real fire in our application. What we have is a PCB and the connector and the cable. Looks like that. And when we have a look at those thermal disappears, we have a first look at the conduction. And the conduction is done in the copper wire, which is mounted on our connector, and also in the copper traces in our PCB. The convection is going up from the connector, and also radiation is everywhere around the connector. So we want to transport the heat away through conduction. What is the easiest idea to use the conduction? We just use our copper cable. Copper is a material which is very good for heat dissipating. We will see in the next slides. So we have a look a little bit closer on our cable. There's the formula for it. Just the thermal energy in Joule is the power multiplied by time in seconds. When we have a look at the conduction, we can calculate the conduction with the Fourier's law. And yeah, let's say it like this. If the section is bigger, it's more effective. If the length is smaller, it's more effective. And if the lambda is bigger, it's also more effective. That leads to this table, which says us copper has the best thermal conductivity. Then the next one is aluminium. You can remember we have some coolers made out of aluminium. That's the reason why we use them, because of the conduction effect of aluminium. And when we look at the plastic material, it's really low, and the lowest thermal conductivity has our air with 0.025. Best conduction material is copper, so it's perfect to use our wires to bring the heat away. And the bigger the copper wire, the better it is. And we can see here that plastic is bad for conduction dissipation. Next dissipation, it was the convection. We have air convection movement around the surface. The more the surface we have in contact with the air, the more efficient will be the thermal exchange. So there's also a formula for that. It's called the Newton's law. Therefore, we have to respect the thermal flow and the convection coefficient. If we increase the surface in contact with the air, it increases the thermal dissipation. So that means if we have a 3-pole connector, it has a lower thermal dissipation than we have a 12-pole connector. Okay, when we have a look at the next one, it's the radiation. And the radiation can also be calculated with this formula. We also use the thermal flow, and therefore we have the surface emission factor and the Boltzmann constant. And this says plastic material has a better radiation effect than a metal material. So, and if you have a dark plastic material, it has also a better radiation effect than a white plastic material. So for example, if you have a white pen and if you have a black pen and you put those pens into the sun and you wait for, let's say, 20 minutes and take the pens back again, you will see that the black pen is a lot warmer than the white pen, and this is related to the radiation effect. So plastic radiation dissipation is highly better than metal dissipation, and unpolished metal is better than the polished one. So let's some things to remind again. An electrical system must have thermal exchanges, so a closed box is not a good idea. We can see also in later slides. Undercurrent temperature should be stabilized after 10 to 20 minutes. Regarding the radiation, plastic material is better than metal, and rough metal surface is better than polished, and dark surface is better than bright surface. Regarding convection, the increase of the surface in the contact with air will increase the convection effect. Regarding conduction, we have to look at the material, and therefore copper is the best material for conduction dissipation, and we have to increase our section to optimize the exchange here. Let's have a look at our cable and the heat in our cable we have to also to respect. Therefore, we have again some tables, and now it depends where you want to specify your product. If you want to sell your application later to the US American market, you should respect the UL table. It's designed for AWG cables, as you can see here on the left side. And it gives you the current for every AWG, which is common on the market for electronic products. And then we have the IEC 16998-1. This is close to the VDE table we saw before for our terminal blocks. It's for household and similar purposes, general requirements, and for insulated wires. And on the right side, you can see another VDE table, which allows a lot of current, but there we have to be careful. This is not for electronic products. This is for single wires without any insulator. So for example, the wires we can see from house to house in the villages, for those on those wires we can apply a little bit more current because there's no insulation around it, so the heat can disappear into the air and can be cooled from the cable can be cooled from outside. So we have to respect the UL table or the IEC table. Depends if we want to certify our product regarding the US market or the European market. Let's have a look on the wire resistance calculation. This is done quite easy. We have a section in square meters or square millimeters, and we have a length in meters and a resistance of the cable in ohms. So the resistance is the material resistivity multiplied by the length divided by the section. Quite easy. So what's the temperature rise with wire? We did a test with an AWG wire, 50 centimeters long. We put on 2 thermocouples sticked on the copper conductor, but no connector in between. Then we put on the 20 amps as we did it with our connector before. And the result is the following table. If we use a wire size AWG20, it heats up. We can put on a current of 5 amps and it heats up 5 Kelvin. If we use AWG10, we can use a current of 30 amps and it heats up 16 Kelvin. But as you can see, 16 Kelvin is lower than the 30 Kelvin, which is allowed for our connector. That means the delta T decreases proportionally to our wire size, and the wire heats less than the connector. Connector is allowed to heat up to 30 Kelvin. The wire heats maximum 16 Kelvin. But what is the right length to disappear the thermal energy? Therefore, we have to do another test. We have to check it with different cable lengths. So again, the same cable with AWG12, and it's related with, it's put on 20 amps. Sorry. And the terminal plug with 3 poles, 762, and different wire lengths, and 2 thermocouples and 2 TBL clamps. So therefore, we have a connector again, and now we check the cable length and we measure the temperature at the connector. So let's see on this point with a thermal camera. Here we have a quite high temperature at the connector, around 26.3 Kelvin heat. Here we have 19. Here we have also 19, also 19. It goes down to 17, but then it stays nearly at the same level. If we put on a very short wire on the connector, we just checked this with a 2.5 centimeter long wire, we can already see in the thermal view from the thermal camera that this wire is getting really, really hot here, and it heats up the connector in a not good way. So when we do a graph, connector delta T versus the cable length, we see that the ideal cable length is around 10 up to 15 centimeters. The cable is longer than 15 centimeters, doesn't make sense, it's useless for the thermal dissipation, but less will increase the internal connector temperature, so please put on your cable at least in 10 centimeters length. The right size of the cable, we did another test. We used 3 different wires, an AWG16, an AWG14, and an AWG12, and we measured the internal connector temperature rise, and with AWG16 it was 17 Kelvin, with 14 it was 10 Kelvin, at 12 it was 8 Kelvin. So, but also the price is different. That means increasing the wire size decreases our delta T, but the cost decision is yours. What do we have to remind regarding the wires? Copper wires heat less than connectors. Wires are used to dissipate the heat out of our connector, and the optimized length is 10 to 15 centimeters. Now I have some additional tricks for you. First of all, what's with the polarity? Working current is always tested with 3 poles. That's what UL says. So, when we have, for example, a 12-pole connector, should we decrease the current? You remember we have more poles, so we have more points which will be heated up by our current. So normally this curve should go up like this. This is what we are expecting. But when we do the measurement, it's completely different. It doesn't heat up that much because we have more surface to dissipate heat in the air. And we have a security margin. That means at the end, thanks to our security margin, working current could be used for any number of poles. So if you have a 12-pole connector or a 24-pole connector, it doesn't matter. You can use it with the same current as the 3-pole connector. When we put a connector in a closed box, we saw it at the beginning of the presentation. It was not a good idea. Yeah, because the connector temperature is rising very fast and the box internal temperature is also rising very fast compared to an outside connector, as you can see on this table. And the most important thing, the time for the stabilization takes a long time in a closed box. What can we do? We can, for example, put some holes in the box. Thermal energy is stored in the box, not enough exchanges. We put some holes in the box. Same with closed box with holes. It's a little bit better, as you can see. The connection temperature is not that high as before with the internal wires, but the box internal temperature is also getting a little bit down and the time for stabilization is much lower. So it is not a bad idea to have some holes in the boxes. But as you know, this is not possible in every application, so we have to look for further possibilities. Holes and convection decrease stabilization time and temperature. Now we take the same box and we put the wires outside from the box, external wires. So remember, the wire brings the temperature away from our connector, and when it's outside the box, it brings it also outside of the box. So this looks also much better than before. Also, the time for stabilization goes more down again, means the external wire adds to the conduction effect, and it's a better effect than holes in the box. We did a last test. We just reduced our current. The same closed box without any holes, without any wires outside. We put on 15 amps instead of 20 amps. And as you know, the I-square rule, this is the best solution we can do. So the time for the temperature stabilization goes down very fast and the connector heating is very low. So the best way is to decrease current. So if you have a closed box, you can choose if you put your wires outside. The best way is to decrease current if you are able to, or put a connector inside which is suitable for higher currents, for example. And also the wires, sure. There are different possibilities if you have a closed box, and I hope I could help you a little bit with those hints. So what do we have to remind here? The working current is for all pole numbers possible, and in a closed box, maximum of cable has to be put outside, and oversized cables and connectors, please. Should I decrease connector current after several mating cycles? It's also a big question the customers sometimes ask us. Yeah, delta T will increase after some mating cycles. Normally it should be like this because when you remove the plating material, you normally get a higher resistance. But in this case, the security margin of the Würth Elektronik products is very high, so the resistance goes up very low. So it doesn't matter if you have 25, for example, mating cycles in the data sheet, and you go up to 40 mating cycles. It doesn't matter. The resistance doesn't go up. So you can use also after 25 mating cycles, you have close the same resistance than if you have a brand new connector. That's because of the security margin of Würth Elektronik. When we have a look at the connector which has a screw clamp inside, some people think if they tighten the screw very high with a high torque, it must be better, the resistance must be lower. Is this true? No, it's not. We took a rising cage connector, and it's the same for a spring clamp connector. If we put on more torque than in the data sheet, it just stays at the same level. So we should respect the torque, because if we do not put on enough torque, the resistance is higher. But if we respect the torque on data sheet, it's quite okay, and the resistance is good for application. So now we come to our derating curve. Regarding the UL curve, we have to respect different things. The maximum connector temperature. At the terminal block, it was, for example, 105 degrees, and the 30 Kelvin for the allowed warming of UL, and the I square rule. There I have an example for you. This is a wire-to-board connector, a cheap wire-to-board connector. It's suitable for 7 amps, and it has an operating temperature up to 105 degrees. And when we now have a look at the UL derating curve, we have to take the black graph because of 105 degrees, and we want to know when we have around 90 degrees in our application, how many current can I put on this connector. It's quite easy to read out here. If we have 90 degrees in our application, I can put on 70% of the related current, and in this case it's 4.9 amps. And the same thing you can do with the VDE derating curve. Here I have the example of our terminal block, a 3-pole terminal block. It's suitable up to 120 degrees, and it has a rated current of 24 amps. We have the same situation. We have 90 degrees in our application. We want to know how many current we can put on this connector with 90 degrees. We can just read it out of the table. It's in this case, it's a little bit more. It's 88%. That means 21.8 amps is possible for this connector. Regarding VDE. Regarding UL, it would be a little bit lower because the American market is a little bit conservative at this point. So what we have to remind again, the number of mating cycles does not take any influence on our delta T. Also, when we screw the TBL hardly above the tightening torque, it has no effect on the delta T. If we decrease current with the derating curves, when you are close to the maximum operating temperature, you're always on the safe side. So at the end, I will show you some connectors which are handled in the wrong way. So for example, we have here also a wire-to-board connector called MPC4. It's suitable for 9 amps at 105 degrees. What did we do? We put it on 35 amps. So more than 3 times. And this it destroys the connector at the end. But we have a horror current. We have a working current 3 times higher, but there was no fire on the connector. And this is important if you want to sell the connector, for example, to glow wire applications, to household machines which are running without any people standing there. We just made another test with the MPC3 series. It's suitable for 5 amps. We put on 16 amps. It also nearly burned, but it melted, but there was no flame. So that means also a horror current, but a working current, 3 times higher, but no fire established. So finally, what to remind. Working current is designed at Würth Elektronik regarding UL with 30 Kelvin, regarding VDE with 45 Kelvin warming. Use the derating current when you are close to the maximum of temperature. Thermal dissipation and the current temperature should stabilize after 10 minutes. Use working current for all pole numbers. Doesn't matter if you have 3 pole or 12 pole or 20 pole. The wire heats less than our connectors itself. The wires are used to dissipate the heat, and the optimized length is 10 to 15 centimeters. In a closed box, put the wire outside and oversize the wires. We have security margin, and it's huge for our connectors, so the plastic is just melting, but it's not burning. That means what we have to do here is create the thermal exchange with outside. So that was the end of my presentation. Thank you very much for listening.
So, thank you very much for your presentation, Stefan. As you have mentioned, now we would like to turn our attention to your questions. So we wait a little until some questions come in. So you can just ask us the question with the webinar control panel, and you will find the chat option there. So then we have a look at the first questions. Stefan,
Yes.
what about the PCB tracks? Can I optimize these two in my application?
Yes, that's quite a good question. Regarding the PCB tracks, we didn't show anything in our presentation, but this has a reason. We are just doing those tests. But what I can say at this point is already, if you use a white PCB track, it has more effect on the thermal dissipation and as if you use a long PCB track. So try to use a very thick and white PCB track. This would be the best for the thermal dissipation through the copper of your PCB. But you also have to respect the other components on the PCB, not to destroy any components because of the heat of this connector. We are doing these tests. I think at the end of the year, we are ready with the test and we can tell you more about it. If you want to write me an email, I can give you the answer of the test at the end of the year and tell you exactly what we can do regarding our PCBs.
Okay, thank you for your explanation. Then
Welcome.
let's go on with the next question. Stefan, do you offer derating curves only for power connectors or for every connector?
Let's say like this, we offer derating curves for power connectors first, because when you use a power connector, you have to deal with a lot of power, you have to deal with a lot of thermal energy. But if you need derating curve for a signal connector, it's also possible to do it. So please, in this case, just write me an email or your local FAE in your country, and he will assist you gladly and create a derating curve also for a smaller connector. It is possible, but it's not mentioned in the data sheet because it's very important for the power connectors and it's not so important for the signal connectors. The only connectors we do not offer derating curves are RF connectors because there are other values important like the losses and the S parameters. Therefore, there you can have S parameters, but there we have no derating curves. It doesn't make sense for those connectors.
Okay, thank you.
You're welcome.
So then as we have a look at the next questions, just a hint from my side, you will receive the link to the presentation as well as to the recording of this webinar only in the next few weeks. So then let's go on. Next question. Does it make sense to use a ferrule on my cable regarding the resistance?
This is also a really, really good question. So it's normally you can use a ferrule in your application. All our connectors are specified for solid wires, for stranded wires, and also for the ferrules. But you have to take into consideration when you put on a ferrule on your cable, you have a crimp. You have to crimp it on your cable, and this crimp has also a resistance. And if you are close to the maximum temperature in your application, I would not recommend to use a ferrule because you have additionally resistance because of the crimp you do on the ferrule.
Okay. Then, Stefan, next question. What is the security margin Würth Elektronik provides?
The security margin Würth Elektronik provides is at least 20% regarding all our connectors.
Okay, short and easy answer. Perfect. So then, Stefan, I see another question here. I think for now maybe it's the last question. We will just wait if another question come up. So I want to sell the application to Canada. Which standard do I have to use?
Yes. If you want to sell your application to Canada, you have to use the Canadian standard, but the Canadian standard is close to the US standard. That means our connectors are certified CLUS, so also for Canada and also for the US market. So then you have to respect the UL table if you want to sell it to Canada.
Mm-hmm. So thank you very much for your explanation.
Welcome.
So now we are finished with our webinar. If there are any questions left after the webinar, you can also just email us at eisos-webinar@we-online.com. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Stefan, for this great webinar.
Yeah, thank you for joining the webinar, and have great days. And please, if any questions are coming up, please write me an email, or you can also ask your local FAE in your country. He will also be glad to assist you in this point. And I have another recommendation for you. If you're dealing with power and high currents, we have also an application guide on our website. It's called the Derating of Connectors. There you can also read a lot of things you saw today in the presentation, and this will help you also with your application if you have to deal with high currents. Thank you very much for listening, and please stay healthy all, and bye-bye from my side.
Also from my side, goodbye.